Alright, so in this segment we're going to look at another problem where we have currents flowing in the presence of magnetic materials. Perhaps a slightly more complicated problem than we studied in the last section, but very similar in its spirit. What we're going to have a look at is a cylinder, again a cylinder of magnetic material, and we're going to have a current density that flows in this material, and the current density is going to depend on the radial coordinate, and I'm going to call that radial coordinate. In this case, I'm going to call it, let's call this one R. So usually we use this for spherical, but it's easier for me to write an R, so I'm going to make it R this time. And by that, as I said, I mean the distance, the radial distance outwards from the central cylindrical axis. So the current density that we're going to consider is a Gaussian current density of the following form. Okay, now the z hat direction is going to be along the cylindrical axis, so I should make that clear. Let's make that z hat. Okay, and before I go any further, I'm going to normalize this current density. I'm going to integrate the current density across the full surface area of the cylinder. So I'm going to take a slice through this, and I'm going to integrate the current density and set it equal to I0. And this is really just for convenience. I want to express this quantity, this constant J prime, in terms of the total current that is flowing down the cylinder. So let's do that. It's not a necessary step, but it's kind of useful. So our dA is going to be the following. Okay, so there we go. There's our integral. Oh, I need to set this equal to. I'm going to set this equal to I0. This is going to be the total current flowing down the magnetic material. And I've given the magnetic material a radius b, so that's this radius out to the outer edge here. This is b from the center to the edge. And let's see, I think that's it. I think that's the normalization integral. The phi is easy, that's just a 2 pi. And the integral over r I would do by change of variables. If I put x equals r squared, then dx is equal to, x is equal to 2r dr, and I can complete that integral. And you should go and do that. I'm not going to do that integral, but if you do that integral, you will get the following relationship between J prime and I0. Okay, which makes our current density then the following. Okay, so there is our normalized current density, and really at the moment we haven't done a great deal. We've just expressed J in terms of the total current flowing through the magnetic material. But that's as you'll see, that has some utility to it, particularly when we try and check the results at the end of the problem. Okay, so let's turn our attention now to calculating H and M and B, and we're going to do that using Gauss's law. And this time in Gauss's law, Ampere's law. This time with Ampere's law, we're going to have to integrate both sides of our equation. So we have the integral of H dot dl is equal to I enclosed, but I enclosed in this particular case is going to depend on the radius of the Amperian loop that we put in, because the loop is not going to, I'm going to make that loop a loop of radius r, that loop is not going to enclose all of our current. So we've got to integrate both left-hand side and right-hand side of the equation. Well, the right-hand side of the equation I've actually already done in the normalization integral. And you'll see that on the previous page. Instead of having an e to the minus alpha b squared, we get an e to the minus alpha r squared. But you should check that and complete that. And if you integrate left-hand side around the loop and right-hand side of J, the integral of J dot dA across this area, you'll get the following result. Okay, so There's our result for H, and at this point we should just check it in some sort of sensible limit to see that it's true. First of all, is it dimensionally correct? Well, yes, it is. The terms inside the brackets are dimensionless. They have no units at all, and so H is proportional to current divided by distance, and that makes sense. All right, what about if we were to look at R equals B? Well, at R equals B, this term in brackets is equal to this term in brackets, and we can just divide those through, and H is equal to the total current divided by 2 pi R at the surface at R equals B. So it would actually be I0 on 2 pi B, and that makes perfect sense because our Amperian loop would be enclosing all the current. So this makes sense. Now, those two quick checks give us some confidence that we've actually done the mathematics correctly. All right, so at this point, we can calculate our equations for M and for B. So let's do that. Okay, so there then are our equations for M and our equation for B, and you'll notice of course B has the same form of H, aside from the fact that there's a mu naught here, and our total current has this active factor of chi. This is the 1 plus chi. The chi bit is due to the bound currents and the 1 bit is due to the free currents.